So we spent a lot of time talking about limits so far, and the reason limits are so important for us here in the beginning of calculus is to help us better understand the next big idea of calculus, which is a derivative. I've mentioned a derivative a few times here and there, but it's a really important idea for this class. We're going to talk about it for the next 2 chapters, so buckle up, get excited, here we go. But before we start to talk about the derivative, we should talk about what the derivative's actually trying to tell us, because that's just as important, if not more important. So to do that, I actually want to think all the way back to section 2.1 when we talked about this idea of average rate of change. If we wanted to know the average rate of change on an interval a to b, we said, oh, well, you can find that using this formula, f of b minus f of a over b minus a. So here I have just some average rate of change between b and a. We also said that that tells you the slope of the secant line as well. But rather than go with AB right now, notice my interval this time I have a to a plus h. So the way I sort of think about this interval is I say, okay, here I have a, and then I have a plus h. So if I were to view this on my number line, let me draw that out. So here's a, and then some unit away right here, this guy over here is a plus h. So I've moved a total of h units away. Now I don't know what h is, and it doesn't even necessarily need to be small right now. It will become small as we see here in just a second, but if I want to know the average rate of change of our function f of x on this particular interval, this formula didn't just come from nowhere. We just kind of applied our average rate of change formula. We said f of a plus h minus f of a divided by a plus h minus a. I really have two almost two terms in the denominator. I have a plus h for this guy right here, and then I've got a for this x value right here. And then hopefully we look at this and say, okay, well, a and a, those two cancel, and then we have f of a plus h minus f of a, all of this divided by h. So that's where that formula comes from. So this is what tells me the average rate of change, right? This tells me the average rate of change from a to some other number a plus h. And that's all well and good. But now I want to think about, okay, what happens if this h? What happens if this distance, because remember that this whole distance right here, this is h. What happens if I take this distance right here and make it smaller and smaller and smaller and smaller? What happens if that distance between those 2 points gets really tiny? What happens? Well, here's the big kind of the big kicker here of this section. We end up with this thing called the instantaneous rate of change, is the limit as h approaches 0 of f of a plus h minus f of a, all divided by h, which also tells you the slope of the tangent line if the limit exists. And this is huge. This is something that we actually sort of hinted at way back in section 2.1, but we didn't quite nail down this idea. So I want to draw it here. Let me see if I can give a good example. So here, if I have some function, right, it doesn't matter what the function looks like. Let's pretend it's, well, we're going to look at a quadratic here in just a minute, so let's stick with that. And let's say I've got this point right here. This is a. And then I've got another point over here, a plus h. So this point right here, this is the slope of the secant line. Here is a plus h. And this distance right here, like we said earlier, this is h. So that's the slope of the secant line, but imagine for a moment that I'm really interested in slope of the tangent line. I'm really interested in saying, okay, how can I take that blue line and make it as close as possible to the red line that I've drawn in here? That red line is the tangent line. Well, we probably don't want to move this x value right here because they already passed through that same point. It seems like we should kind of have that same shared point if we want to pass through that same or have the same tangent line, right? If we want the blue line right here to fall right on top of that red line, we probably don't want to change this point right here. It's this point over here that maybe is a little bit of a problem. So, okay, how can we take this approximation and make it a little bit better? Well, we might say, okay, well, what if you took this point right here? What if you took this point and moved it a little bit closer? So now I have this blue line. Let's actually erase the old one. So now, okay, now my blue line is a little bit closer, but it's still not right on top of it. How could I make this approximation a little bit better? And it's going to get a little messy here just because I don't have a ton of room. But if I put another point right here, if I move just a little bit closer, I end up with something that looks like this. And that's a little bit closer. So what's happening to the h, right? So if h is this distance, I took h and I shrunk it down a little bit, and then I took it and I made it even smaller. So as I make h smaller and smaller and smaller, the blue secant lines are getting closer and closer to that red tangent line. So if I want a perfect approximation, I would want to look at the limit as h approaches 0. So what happens if I make that distance virtually 0? What does that look like then? And then that would actually tell me the slope of the tangent line. That's what I'm interested in at the end of the day, is how can I find the slope of the tangent line? What I really want to get to, whoops, erased my line here. What I would really like to know is how do I find the slope of this tangent line, this red tangent line, because that tells me all sorts of really cool information. So if this didn't make a whole lot of sense, let me try another graph here to show what the derivative is actually trying to tell us, and you can actually go and check this out for yourself. If you look up just limit definition of the derivative on Desmos, you'll come up with this graph right here. Notice on the left-hand side, number 7 is a. I'm going to have a just be 1, just for the sake of easiness. And then h, remember that's the distance between these 2 points. So a is just this point right here that I've taken and I've now moved just a little bit, and this is the point that I want to find the slope of the tangent line at. So I could move it all the way down here, I could move it right here. That point seems kind of important. Might be something we think about later on, but let's just say for the sake of argument right now it's right around 1. And h is the h is the distance between that point there that is fixed and then some other point. So if I want to sketch in that blue line is the tangent line. That's what I'd really like to know. I don't know how to find that yet, but I do know how to find, this red line. This is the average rate of change, the secant line. We know how to find that. We can use our average rate of change formula. But the idea here is that if we want to use this red line to help us get as close to that blue line as possible, if I take this other point over here and I move it as close as possible, watch what happens to h right here. Watch what happens to h in number 6. If I take this and I move it closer and closer and closer and closer, okay, well, my red line is getting closer and closer to the blue line, which is exactly what I want. It's falling almost right on top of it, and what's happening to h? That h is getting smaller and smaller and smaller and smaller until all of a sudden, hey, look at that. Now I have pretty much the exact same line, which is what I want. Same thing happens from the other side too. If you wanted to start over here, now h is just a negative distance, which means it sits on the left side of a. But again, as I take that point and I move it closer and closer, the red line gets closer to the blue line, and h gets closer and closer to 0, this time just from the negative side. So that's exactly how I find the instantaneous rate of change, or the slope of the tangent line. So this is going to be really important, and let me highlight the part that I want to focus in on here. The instantaneous rate of change, I just take the limit as h approaches 0 of the average rate of change. So I want to practice using this formula here. in example 1, it says, find the equation of the tangent line of each function at the given point. So I'm going to use this idea of the limit as h approaches 0 of f of a plus h minus f of a divided by h, because this tells me instantaneous rate of change, instantaneous rate of change, and it also tells you slope of the tangent line. So if I want to write the equation of the tangent line, in order to write the equation of a line, I need two things. I need a point, which was very generously given to me here, so I have a point. That's good. And I also need a slope. So I need this slope of the tangent line. Well, how do I find that? I find it using this limit statement. So if I can find this limit, that will tell me the slope of the tangent line, and then I can use that slope and this point that they gave me over here to write the equation of the tangent line. So let's get to it. Let's just hop right in. Now I could go and plug everything in here at once, and there's nothing to stop you from doing that, but I think that this phrase can look a little bit intimidating. There's a lot happening there. So I usually break that down into a few steps here. I'm going to walk through it here. So the first step I'm going to look at, I'm just going to look at this piece right here, f of a plus h. And a in this point, that's the x value that we're talking about. So a in this case is just 3. So I'm going to look at g of 3 plus h, and I'm going to just figure out what this is. So I'm going to take 3 plus h, I'm going to plug that in for x. So I have 3 plus h, quantity squared, minus 5. And here I'll have to square this, I'll have to FOIL this out. This really says 3 plus h times 3 plus h minus 5. So if I FOIL this out, I should have 9 plus 6h plus h squared minus 5. And then 9 minus 5, that's really 4 plus 6h plus h squared. So here is my result for g of 3 plus h. Once you get to a point where you can't simplify this anymore, then okay, I'm going to move on to the next step. I'm going to see, okay, what do I add next? Or rather, in this case, what do I subtract next? Well, I subtract f of a. So I'm going to go find, first of all, in step 2 here, I'm going to find g of 3, because 3 is my x value. 3 is my a value that I'm talking about here. So g of 3, this is 3 squared minus 5. This is 9 minus 5, which gives me 4. So if I want to look at g of 3 plus h minus g of 3, which, look at this. This is actually just my numerator. If I obviously f and g are different functions, but it's the same idea here. But a here is just 3. All I've done is take 3 and plug that in for a. So I'm just looking at the numerator of that statement. So g of 3 plus h, this guy right here, well, that's just what I found at the end of step 1. So I'm going to start with that. So 4 plus 6h plus h squared minus g of 3, well, we just found that. That's 4. So okay, we'll plug that in next. So minus 4. And hopefully we look at this and say, hey, you know what? I've got 4 minus 4. Those two can cancel. So I'm left with simply just 6h plus h squared. So okay, we get to this point where we can't really do much more, so maybe we'll try something else. Well, what else do we have? Well, we also divide by h. So let's go ahead and do that. So I'm going to take, I'm running out of room here, I'm going to take what I just found, so g of 3 plus h minus g of 3 divided by h. So this piece right here is just what I found at the end of step 2. I'm going to take that and plug that into the numerator of this function here. So this is 6h plus h squared divided by h. And our goal is to simplify this as much as we possibly can. I see a common factor of h in the numerator, so I can factor that out. That'll leave me with 6 plus h divided by h. And then we'll look at this. Again, I have h in the numerator, h in the denominator. I can cancel those out, and I'm left with just 6. Oops, excuse me, 6 plus h. Almost forgot my plus h here. So that's as much as I have, and at this point I have almost everything. The only thing I'm missing is this limit statement right there. So that's the last thing I'm going to add on here. So the limit statement, let me actually erase this so that we have some room. So now this fourth step, I'm just going to take the limit as h approaches 0 of g of 3 plus h minus g of 3, all of this divided by h. Well, this piece right here, I already know it. That was the same as this piece right here, which is just 6 plus h. So I'm just looking at the limit as h approaches 0 of 6 plus h. Well, this is nice and easy. There's really not a whole lot to do here. Just plug 0 in for h. 6 plus 0 gives me a positive 6. So this is my result. So it's a pretty lengthy process, and it's easy to lose track. What did we just find? Remember, this is the slope of the tangent line. So this is slope of the tangent line to our function g of x at x equals 3. So it's the slope of the tangent line to the function g of x at x equals 3. Right now, I just want to focus on slope of the tangent line, and actually just slope. So we have the slope. We have our point, right? Think back to what we wanted to do. We wanted to find the equation of the tangent line. So I have my point. I have my slope. I have everything I need. I can go write the equation of this line. So let me do that right here. Oops. Let me do that right here. For writing the equations of lines, you can either use point-slope form or slope-intercept form. I prefer point-slope form, which says y minus y1 equals m times the quantity x minus x1. That's my preferred notation, but if you would like to use slope-intercept form, use y equals mx plus b, by all means, feel free to use that. But if I use point-slope form y minus y1, that's just going to be, let me erase this so that I can kind of point at it. y1, that's just the y value of our point, so y1 is going to be 4 here. So y minus 4 equals m. Well, that's the slope that we just found. That's m equals 6. So I'm going to plug 6 in. 6 times x minus x1. x1 is the x-coordinate of the point that we have, which right here is just 3. And there we go, y minus 4 equals 6 times the quantity x minus 3. If you want to, I believe my math lab will be fine with you leaving your answer like that, but if I actually don't remember, they may want you to write it in slope-intercept form, in which case we just need to solve this equation for y. So I'll do that real quick. I'll distribute my 6 over here. Y minus 4 equals 6x minus 18. And then add 4 to each side. Y equals 6x minus 14. This is the equation of my tangent line. So this is something we're going to be doing a lot of. We're going to be looking at, well, what's the equation of the tangent line, or what's the slope of the tangent line? So I would get a lot of practice with these, and I would try to remember that really it's just the limit as h approaches 0 of that average rate of change. That's all we're doing. We're taking that average rate of change, we're taking those 2 points and we're moving them closer and closer together until the secant line approximates the tangent line. So take a look at some of these examples. We are going to be doing quite a few of these in the sections to come.